We're about to uncover the shocking truth about a force that's all around us every single day. We're talking about static electricity, from that tiny little zap to a massive thunderstorm.
You totally know the feeling I'm talking about, right? The crackle of a sweater when you pull it over your head, or that sudden, sharp zap from a doorknob. Well, it turns out those aren't just random, weird little annoyances. Nope, they're actually clues to one of the most fundamental secrets of the entire universe.
So what's the deal with those zaps? The reason behind all of it is something called electric charge. And it's not some far-off, complicated thing. It's a basic property of the tiny particles that make up, well, everything. You, me, the chair you're sitting in. So today, we're going to break down exactly how it all works.
Okay, so let's dive into the world of electrostatics. It sounds fancy, but static just means we're looking at charges that are, well, stationary. They're just hanging out, not moving around in a current. But don't let that name fool you, because even when they're just sitting still, these charges pack a serious punch.
All right, so here's our game plan for today. First, we're going to meet the two different types of charge. Then we'll see how they behave in different materials, learn the three big rules that they always follow, and finally, we'll figure out how to measure their incredible power using something called Coulomb's law. Let's get into it.
Okay, first up, what is this charge we keep talking about? Well, after a whole lot of experiments, scientists figured out that it basically comes in just two different flavors. And you can thank none other than Benjamin Franklin for giving them their names, positive and negative. He saw that if you rubbed a glass rod with silk, it got one type of charge. He called that positive. And if you rubbed a plastic rod with fur, it got the other type. He called that negative. Honestly, the names themselves are kind of random, but hey, they stuck. Now here is maybe the most important rule in all of electrostatics, and it's so simple. Likes repel and opposites attract. That's it. So if you have two positive charges, they're going to push each other away. But if you have a positive and a negative, they're going to pull right towards each other. This one single rule, it's the key to pretty much everything we're talking about today. Okay, so we've got positive and negative charges, and we know they attract and repel. But that brings up a question, right? Why is it that when you run a plastic comb through your hair, it gets all staticky, but if you try the same thing with a metal spoon, nothing happens? Well, it all comes down to how different materials handle charge.
And materials basically fall into two camps. First, you have what we call conductors. Think of these as electron highways. Charges can just zoom right through them, no problem. Metals, your own body, even the Earth itself are all great conductors. Then you have the opposite, insulators. These are more like electron traffic jams. They put up a huge fight and don't let charges move around easily at all. We're talking about things like glass, plastic, and wood.
Okay, so with that in mind, let's go back to our little puzzle. Why does the plastic comb get all charged up, but the metal spoon doesn't do a thing? Well, here's the answer. It's because both you and that metal spoon are conductors. Any extra charge that might build up on the spoon has an escape route. It flows right through the metal, through your body, and safely into the ground. But that plastic comb, it's an insulator. It doesn't let the charge escape. It holds onto it, building it up. And that's why you get that crackle and zap.
All right, next up, we're going to get into the three fundamental, absolutely unbreakable rules of charge. If you can get your head around these three things, you'll have a really solid grasp on the basics of all electricity.
Okay, rule number one, additivity. This is easy. Charges just add up like simple numbers. So if you have +2 and +4 and -3, your total charge is just +3. Simple. Rule number two, conservation. This is a big one. You can't create or destroy charge, ever. You can only move it from one place to another. And rule number three, quantization. This one's a little weird. It means charge comes in tiny, discrete little packets. So what on earth does quantized actually mean? Let's dig into that a little more. Think about it like money. You can have 1 cent, or 2 cents, or $1,000,023, but you can't have half a cent, right? It just doesn't exist. Charge is the exact same way. It comes in these tiny, fundamental, indivisible packets. You can have one of them or 1,000,000,000 of them, but you can never, ever have half of one.
You know, there's a really great analogy for this. It's like looking at a dotted line from really far away. Up close, you can see all the individual dots and the gaps between them. But from a distance, it just looks like a solid, continuous line. That's exactly what's happening with charge. There are just so many of these tiny little charge packets, even in a small spark, that we never notice the gaps. To us, it just looks like a smooth, continuous flow.
And when we say these packets are tiny, we mean unbelievably tiny. The amount of charge in a single one of these packets, the charge of one electron, is that number right there. It's so small it's basically impossible to wrap your head around. I mean, you'd need trillions and trillions of them just to light up a light bulb for a second. So yeah, no wonder we don't notice the individual grains of charge in our everyday lives. So we know charges attract and repel. We know they move through conductors and get stuck in insulators, but how strong is that attraction and repulsion? Can we actually put a number on it? Yes, we can. And this brings us to the grand finale of our journey into electrostatics, a law that, as you're about to see, looks shockingly familiar.
And the guy who cracked this code was a French physicist named Charles-Augustin de Coulomb. Back in the 1780s, using a really clever and super sensitive device, he was able to actually measure the incredibly tiny forces between charged objects. And what he found out pretty much changed our understanding of the universe forever.
What he discovered boiled down to two really key things. First, the more charge you have, the stronger the force. That makes sense, right? Bigger charges, bigger push or pull. Second, the force depends on distance. And this is crucial. The force gets weaker the farther apart the charges are, and it drops off fast. If you double the distance between two charges, the force between them doesn't get cut in half, it becomes 4 times weaker. That's called an inverse square law. Okay, and this is where it gets really interesting. Take a look at the formula for Coulomb's law. Does it look familiar? It should. It's almost identical in its structure to Newton's law of universal gravitation. They both follow that same inverse square rule. But there are a couple of huge differences. For gravity, the driving property is mass. For electricity, it's charge. And the biggest difference of all, gravity only ever attracts. It only pulls. The electric force, it can both attract and repel.
So that sets up a kind of cosmic showdown, doesn't it? We have these two fundamental forces of nature, and they follow almost the same playbook. So which one is stronger? Which one is the true heavyweight champion of the universe? Is it gravity, the force that holds planets and entire galaxies together? Or is it this electric force?
Well, get ready for this, because the answer is absolutely mind-blowing. It's not even close. The electric force between a single proton and a single electron is, well, just look at that number. It's trillions of trillions of trillions of times stronger than the gravitational force between them. The electric force isn't just in a different weight class. It's playing a completely different sport on a different planet. It's just staggeringly, unbelievably powerful. All right, so let's just do a quick wrap-up of the key takeaways. We've learned that matter has this property called charge, which comes in 2 flavors, positive and negative. We know that opposites attract and likes repel. We figured out that conductors let charge move freely, while insulators keep it locked in place. And finally, we saw that the electric force, which is described by Coulomb's law, is just mind-bogglingly strong. But that leaves us with one final giant puzzle, doesn't it? If the electric force is so ridiculously, absurdly stronger than gravity, then why is gravity the force we notice all the time? Why is it gravity that's holding you in your chair right now and keeping the Earth orbiting the sun? Why don't we feel this immensely powerful electric force all the time? Well, the answer is actually hidden in everything we've just talked about. Something to chew on.